Hello, everyone. My name is Wang Yong. I work for ZTE Corporation. Today, I'd like to share some of my experience about DPDK used in containers. I will talk about some of the challenges and give some solutions or suggestions. First of all, I will show a picture. This is a simplified typical use case of our app in containers. We used DPDK 18.11.1. And in this picture, we can see there are 3 containers. We call them C0, C1, and C2. And we use this the primary, secondary mode. The C0 is the primary, and C1 and C2 is the secondary. We used shared memory to achieve the zero copy. And we used RT ring to achieve the queue between containers. Let's see the first challenge. It's namespace. We used this is some of the containers DPDK parameters. And C0 is we used prototype is primary, and we used the file prefix, the RTE C0, and all the containers will use the same file prefix. And C1 and C2, they are the secondary. Let's see what happened when we run. C0 will start up, OK. And C1 start up, OK. And C2, well, we met error that EL cannot initialize local memory. Start or fail. Let's see the MP socket file. The third part of the MP socket file is the process ID. It's 44 in C1. And we can see in C2, the process ID is 44.2. They are the same. It's a PID conflict. How does this happen? We know that in containers, there are several namespaces, such as UTS namespace, such as net namespace, PID namespace, that is, and works here. Each container has its own PID namespace. PID of the app in different containers may be the same. And the DPDK has a function named secondary MSL, create work. It uses the PID to distinguish the FB array of different secondary. So just like this code shows, get PID. When app in the C1 and C2 have the same PID, error occurred. And how to resolve this? We have 2 solutions. The first one is if we use Kubernetes and the C1 and C2, the secondary containers are in the same pod, we can set a parameter named share process namespace, set the value to true. Then the PID of different secondary process will be different. And this is in C1, the process ID is 44.2, and in C2, the process ID is 47. They are different. And the second solution is our choice. If the Kubernetes is not be used, or the secondary containers are not in the same part. How could we do? We just modify the function. We add the RTE, RDTSC to get the cycle to distinguish FB array of different secondary, just like this. And let's see the challenge 2, mmap fail. Sometimes when we run the primary secondary process of DPDK in containers, we met mmap fail. Sometimes it's not. C0 startup OK, and C1, we met a panic. Cannot mmap memory for RTE config at this address. How does this happen? Let's see the DPDK mmap in multiprocess. The RTE config in the disk, mmap will map this file to cache, to memory, and to the container process namespace. The primary process manages all the DPDK resources, and the secondary process will attach to the resource. And they will use the same process address, the virtual address in the container namespace. Why secondary process mmap fail? The primary process mmap without specify the address. So they use the address, the Linux kernel alloc for the mmap. It's always a very high address, such as the 7F billion in hexadecimal. No. And when secondary process mmap the same address, what if the address have been used by other file, such as other dynamic libraries? When this thing happened, the secondary process may mmap fails. How to avoid this? There are two solutions too. The first one, just as the DPDK community suggests, we can use the base virtual address option to specify the mmap address. We can specify the base virtual address to 20 billion, maybe, in hexadecimal. That is distinguished with the 7F billion in hexadecimal that Linux kernel specify. This can avoid the conflict. And the second solution is our choice. The DPDK has provided a function named EAL, get virtual area, to get an available lower address in the process virtual address space. We just modified RTE EAL config create, call the EAL get virtual area to get an available lower address than primary process and map the address. So EAL get virtual address area always find an available address starting from the maybe 10 million in hexadecimal. It's a very low address. It's distinguished with the address Linux kernel use for mmap. Well, let's look at the third challenge. It's deadlock. Well, as we all know, that DPDK is greedy. How to achieve better performance just in terms of threads? We can use the dedicated data path thread. We can use LCPU isolation. And we can set thread affinity. And Not only the DPDK is greedy, the operators is greedy too. And when this greed conflict, the operators always win. The operators always demand better performance just with the limited CPU's number. This will result the VM CPU's overcommitment and containers CPU overcommitment. The result is not all the threads running DPDK in containers could be dedicated, isolated, or set affinity. Our choice is in container 0, the data path thread will use dedicated, isolated, and set thread affinity. And the master thread, we will let it shared. In C1, C2, and Cn, maybe, the data path thread, whether it is dedicated or shared, it depends on the specific service. Sometimes they may be asked the high performance, they will use dedicated. Otherwise, it's shared. And the master thread, it uses shared too. Well, let's see how this thread deadlock happen. And we use RTE mempool, and the RTE mempool use RTE ring, uses lockless mechanism. And we use multi-producers and multiple consumers. And the schedule policy is scheduled FIFO or scheduled RR. And we used a lot of threads with different priority. So let's see this picture. This picture comes from the DPDK's community. It's a part of the program's guide. When we just, the core 1 and core 2 will enqueue object to the queue. They will use a compare and swap to the prod head. And after the prod head is moved, the prod tail is need to move too. But what if the core 1 is preempted now and never be scheduled again? The prod head has been moved, and the prod tail will not be moved anymore. So this is why the thread deadlock happened. And solutions, there are a lot of solutions that DPDK community suggested. The first one is modify the multiple producers to single producer, or choose single consumer to replace multiple consumers. Or we can choose the schedule policy, not use FIFO or RR, to choose schedule other, schedule batch, or schedule idle. Then someone will ask, what if we have to use the preemptible scheduling policies and multi-producer and multi-consumers? We can use the RT stack instead of RT ring. This is also the community suggested. And use the RT mempool stack to replace the RT mempool ring. But it has several because the solution is only available from DPDK the 19.05, and we used just 18.11. And this solution limited to the x86 64 platform because it uses a 16-byte compare and swap instruction. And the most important is it has worse average case performance than the non-preemptive RT ring. So we don't choose this solution. Our choice is add a hypervisor to all the containers, just like the picture shows. This hypervisors, all the processes, threads, tasks using DPDK created by the hypervisor will have the same priority, and the priority is the highest in the system. And the second is all the child processes, threads, subtasks using DPDK created by the process above inherit the priority. So all this can solve the deadlock. And the last challenge is thread affinity. Well, sometimes when we test the performance, we use the containers with the same resource and running the same job, but in different time, we get the different performance. And the performance is unstable. How does this happen? We found that EAL interrupt thread and RTE MP handle, these two threads are spawned to the threads belonging to the other containers. We do an experiment, do a test with TestFMD. We run TestFMD, use these parameters. And for several times, the first time we checked, these two threads used the 20th L CPU, and the second, we found that they used the 12. Neither of these two are in the TestFMD's parameters. And we checked the code of DPDK. We found DPDK EL initialization spawns the control threads on L cores other than part of the EAL core mask. What if the L cores have been used by other containers or processors? How to resolve this? We can use just the community suggests we can use task set or CPU set to run the DPDK app, just like this. And we will find that these two threads use the apes LCPU as the task set used, but TestFMD not used. And the next one is task set and TestFMD use the same thread from 1 to 3. And these two threads will use the thread the LCPU 1. But this solution is only available in DPDK 19.05 or later. Our choice, the reality we faced is our DPDK version is 18.11.1. And there are no free cores for control threads. And not all the containers use task set or CPU set. Our choice is modify the RTE control thread create the control thread set affinity to the master L core. This is part of our parameters -L, 0, 2, and master L core equals to 0. Now, another problem is inaccurate timeout calculation. The timeout calculation, we used the value of RDTSC. The return value of RDTSC are different in different CPUs at the same time. And just as I mentioned before, some of the threads are shared, are not dedicated, and are not set affinity. So if the RDTSC is called the first time is in thread 1, and the second time it runs in another L core. So time 2 minus time 1 will get the wrong value. How to resolve? We can use one thread who would set affinity or dedicated is better. We call the RDTSC periodically and write the value to shared memory or global variable. And other threads who want to use will read the value. This is suitable for the scenarios not need high time accuracy because the periodically is not too frequent. And solution 2, we use the hypervisor I described above to provide the timeout interface to all the threads. And this is suitable for scenarios need high time accuracy. And the last problem I want to mention is inaccurate statistics. This is similar to the problem previous one. The states use thread variable and the thread is shared and not set affinity. And the solution is the first one is that use global variables. So it met concurrency problem now. And the second, maybe we can use shared memory, and this is poor efficiency. 2. And what we choose is set thread affinity and use global variable array and use the L core ID as array index. That is, trade space for time. At last, I should say thanks to Trishan. He gave a good advice for my title of speech. And I should say thank you to my teammate, Han Li. And she is a female contributor of DPDK community. She can't be here because of the visa. And I should say thank you to Han Jian. He's my teammate too. He gave some of the experimental data for me. And at last, I should say thank you to Tu Yaqi. He's my leader. He gave me a lot of support, and the most important is he supported my trip, so I could speak here. And last, thank you for listening. Any questions?
On the excuse me, on the I think the first problem you had, is there any reason why that couldn't be upstreamed, the namespace PID?
Yeah.
Does that cause any other problems with non-containers? The very first thing that you mentioned.
Oh. Wow.
Yeah, that one.
Yeah.
So is there any reason that couldn't be upstreamed? Can you upstream that into DPDK, or does this have to stand alone?
Oh, this one, we had committed to the DPDK community. Maybe not. I will check it of this.
And the second one was, you said, I think on the second to last issue, you said task set couldn't be used until DPDK 1905. What was the feature that was using that wasn't available until 1905?
We choose the...
It had something to do with the helper cores, the 2 helper cores that were launched. Helper threads, rather, that were launched. You said something wasn't available until 1905.
Do you mean why we don't choose the 1905?
No, you said you couldn't use task set because something wasn't available until 1905.
Oh,
but
it's another. Because in DPDK 1905 there is a new lib named RT stack. It is.
Okay, I can ask you afterwards.
Yeah.
It was on a different slide.
Yeah.
On 16-byte compare and swap, the support was added for that in, I think, 1905, only for x86 platforms, but that instruction is available on ARM platforms as well. So it should be enabled in 1911 release. So you should have 16-byte compare swap API provided for ARM platforms on 1911, and RT stack library should be enabled in 1911 for ARM platforms.
Okay, thank you. Any other questions?
Maybe one more question.
Yeah, one more question is about, you said, so RT mempool stack, right?
Yeah.
You are not choose that because of the stack up of the performance, and because of it have lower performance.
Yeah.
That's the major concern. And then you introduce to use a hypervisor.
Yeah.
So then, do you have any performance compare between them? Because introduce a hypervisor also gives you extra overhead, right?
Why? We choose the hypervisor. It's not only the performance concern. It's because the hypervisor we used is for several years from the product, just not use the virtualization, and we just inherit the code and migrate it to DPDK.
Okay, thanks. I'm just wondering, so because of the performance. Okay, so thank you.
Okay, thank you. Thank you very much.
Thanks.